Hello and welcome to my presentation on Mildred Gostling and the Fenton reaction. My name is Robert Williams, and hopefully during this presentation I can explain to you who was Mildred Gostling, what is the Fenton reaction, how does the Fenton reaction work, and how is the Fenton reaction still used to this day. So let's begin with who was Mildred May Gostling. Mildred May Gostling was an English chemist who was predominantly known for her work on carbohydrate chemistry. To give a bit of an background on her, she was born in the United Kingdom in 1873, and in 1893 is when she actually attended Royal Holloway College to get her undergraduate degree in chemistry. Due to her status there, she was actually awarded the Bathurst studentship at Newnham College in Cambridge. And it was actually here where she met her advisor, Henry John Hortsman Fenton, who she worked under and published a total of 4 works under his advisorship. And if you recognize the last name Fenton here, this is where this whole project ties into the Fenton reaction, which we'll get into shortly. After her time at Newnham College in Cambridge, she was offered the role of demonstrator at Royal Holloway College, where she completed her undergraduate degree. However, she was only there for a few years as she then got married to another organic chemist. And then after that, she ended up taking a bit of a step away from chemistry to work uh, as a mother and take care of her children. One of my favorite facts about her, though, is that she was one of 19 female chemists who submitted a petition to the Royal Chemistry Society. This society, at the time, only allowed male chemists to be inducted into it, and her, along with the founding of this petition, Ida Smedley, as well as other renowned female chemists such as Grace Franklin and Marta Annie Whitley, signed this petition and sent it in. And even due to their best efforts, the petition did not lead anywhere in 1904, and it was not until 1920 that women were able to be let into uh, the society. If you look at the bottom left of the screen, you'll see the only picture I was able to find of her online, which I just think is interesting that even after all this time, you can still find a picture of Mildred Gostling. So as I discussed, Mildred Gostling produced 4 publishings in her time at Newnham College while she was under the advisorship of Henry J. Hortsman Fenton. As I also said earlier, her works predominantly focused on carbohydrate chemistry, and um, in particular, the reaction of acids with carbohydrates, and the reason that such an intense purple color was observed. So while I do have notes here on each of the publishings she had, I want to focus in on that second one there, bromomethylfuraldehyde. Quite a mouthful. This actually is probably the most predominant of her works under Fenton, as it explains how that compound, bromomethylfuraldehyde, reacts with respective compounds in cellulose, such as carbohydrate, dextroses, ketohexoses, to create colorful products, and how this reaction basically can show that those compounds are present in solution in a given sample. So that is predominantly around where her work fell, using these intense colors to determine the presence of certain compounds that found cellulose, um, such as carbohydrates, were in solution. If you also look to the left of the screen, you'll find a picture of her Holloway workspace, which is where she, as a demonstratorship, worked on some of her own work, her lectures and classes, and just her time as a chemist. So now that we've discussed Mildred Gostling and her interactions with Henry Fenton, I'd like to move on to the actual Fenton reaction itself. So, what is the Fenton reaction, and why is it so important? The Fenton reaction was actually discovered by Henry Fenton a few years before he and Mildred Gostling interacted um, at Newnham College in Cambridge. This reaction takes a species of hydrogen peroxide and reacts that with an iron species to create this hydroxyl radical group. Now, why is this hydroxyl radical group so important? Well, these are extremely strong oxidizing agents. When they interact with an organic compound, they will react and can degrade that organic compound beyond its initial form. So this is important in a lot of reasons. if you have a toxic or carcinogenic or dangerous organic compound that's typically stable, it's going to be hard to degrade that compound to something that's going to be less harmful. But in the presence of a hydroxyl radical group, you can react with that and degrade the compound to something that's a lot less dangerous. This has been deemed, or this compound, this hydroxyl free radical, has been deemed an advanced oxidation process, an AOP. And as I've kind of stated, or at least led to, it has become increasingly important in this degradation of dangerous organic compounds. And you'll be seeing a lot more of this in wastewater treatments and other organic degradations. So now that we know how in words how this reaction takes place, let's take a look at the equation that leads to this hydroxyl free radical being created and how this would react in a solution. For this example, we're going to have a solution without an organic species present and just how it might react in a solution with the iron, hydrogen peroxide, and present water. So I'm going to direct you to this top equation right here, which shows the bare bones, the overall kind of reaction that you will find, which has this ferrous iron compound. Now, this ferrous iron compound typically comes from an iron salt, so an iron sulfate or an iron oxalate. They can come from many sources there. And then you have your hydrogen peroxide, a relatively cheap and attainable chemical. And so what's going to happen is that you're going to oxidize this ferrous salt to this ferric salt right here. And then along with that, you're going to create this hydroxyl free radical. And excuse me, this should say hydroxide, but you're going to create this hydroxide ion as well. This is the overall Fenton reaction that you see if you just Google up the equation. The reason that there's all of these other reactions in here, including this one of the oxidized iron reacting back to its ferrous state, creating this hydroperoxyl and proton. The reason that these ones are here is because this hydroxide or hydroxyl radical is so reactive and the solution is so reactive that it's going to continuously react to these different phases. If you look on the right side, it better explains that. Once you create this radical, it's then going to react again with hydrogen peroxide, create the hydroperoxyl compound. This is going to react with the iron again. It's going to create the hydroxide. Basically, whenever you have a radical, it's going to react relatively quickly due to its electrophilic nature. This is an electron withdrawing group, and it's going to withdraw an electron either singular or if it's in the case of in solution with an organic compound, it'll react to actually add itself onto that compound, adding on the hydroxide. So this, due to its electrophilicity, is going to react very readily, which is why you see all these side reactions that take place in the solution. But in the overall standpoint, I want to focus in again down here when you introduce the organic pollutant. Then with this hydroxyl radical, that's where you get these degraded products. And that's what you're trying to do with the Fenton reaction. Now that we've discussed the overall equation for the Fenton reaction, I'd like to take a look at a proposed mechanism, or technically two proposed mechanisms. I want to reiterate that these are proposed as the true mechanism for this reaction is still debated amongst chemists today, and there's not really a clear, defined process. I've seen many articles and publications that don't even include mechanistic steps. These ones that I was able to find only include it in an environment that does not involve an organic species. So this is the most information that we currently have that I was able to find on the mechanism for the Fenton reaction. So I will do my best to dissect this so you have a better idea of kind of how this works in an aqueous solution and what the byproducts are. So first, we're going to start up here in the top left with that iron 2 species, which again comes from the salt of an iron compound, iron sulfate, iron oxalate, anyways. This is going to break apart the hydrogen peroxide in the middle of these oxygen bonds. That is going to be the first step. However, it's not these electrons aren't going to be shared directly towards one oxygen or the other. Each are actually going to receive their own electron. The one I'll call this the left is going to share that electron with the iron, which is going to actually use one of its own electrons from its shell to create the bond that creates this oxidized iron hydroxide compound. and then the other electron is going to go onto the oxygen, creating the hydroxide free radical. I'll start with the top steps here. So then you will have these species, the hydroxide free radical, which again, in a typical solution with organic compounds, will react to the organic compounds due to its electrophilic nature. This compound, due to its reactivity, is very electron withdrawing, so it's going to immediately try and react with one of the electrons in this oxygen-hydrogen bond to create a molecule of water. This will take place relatively quickly. As you can see here, water is a byproduct, and that will lead this lone electron from this bond to come back towards the iron, which is going to take another electron from its orbital, and then create this iron for iron oxide compound here. Typically, you don't tend to see iron at this high of an oxidation state, but from the research that I was able to do, this is possibly the iron oxide compound that you get at the end, which is the waste product. And in certain wastewater systems, it's almost like the sludge that needs to be removed in order to let the reaction progress. So if we're going to look down this second reaction down here, this second mechanism, you have this same iron hydroxide species, and now we're going to react with water present in solution. The free radical is going to again attack that this oxygen-hydrogen bond, this time in the water. Because due to its electrophilic nature, it's going to attract or react with one of those electrons. This will again create a species of water. And then that electron is going to go onto this oxygen right here. This is where you get an electron transfer from this iron species down here. It's going to donate an electron up to this species to create the hydroxide ion. That is going to then create these species over here. You have that same iron, now at a different oxidation state, hydroxide species, and now you have hydroxide ion. This is going to react in a typical fashion to remove that hydrogen, that is due to its nucleophilic nature. And then this bond over here is going to react down with the iron, creating that same compound from earlier. So these mechanisms are still being debated, still being adjusted to this day, and while there are likely more interconnected steps, this is the best I was able to find regarding how this mechanism takes place. I do want to note again the addition of, or the creation of water, the usage of that hydroxyl free radical, because its reactivity is going to react with what is in solution, which is why you saw earlier all those different steps of it reacting with other species, and then the creation of this iron constituent. This is again the waste product that, unless you are able to rejuvenate this compound, is going to stay constant in solution. It will have to be removed in order to keep the reaction going without mitigating it. So just to quickly go through this again, these are the steps drawn out. You have the oxidation from the iron, from its secondary oxidation state to iron 3, which then creates the free radical. We looked at that earlier. That radical, as I said earlier, would also typically react with the inorganic species. That's due to its reactivity, and that's what its usefulness is for. In this scenario that we only looked at in aqueous species with just the same constituents from the beginning of the reaction. You will then get that electron transfer from that iron 3 to the hydroxide anion to create, the hydroxide anion. And then that hydroxide anion is going to remove the hydrogen from that iron complex, oxidizing it further, and then giving us the water byproduct, as well as that iron waste. Now that we've discussed the Fenton reaction, let's look into some similar reactions that either create similar species, similar functional groups, or react similarly. And when talking about the Fenton reaction, there's no more similar species than the Haber-Weiss reaction. As you can already clearly see, there's a lot of similarities between the Fenton reaction, up here as I showed you earlier, and this Haber-Weiss reaction. The main difference is that instead of reacting the iron species with the hydrogen peroxide to create the hydroxyl free radical and hydroxide, as you see in the Fenton reaction, you are going to be reacting this oxygen radical anion species called a superoxide anion. This, of course, you can see happens in the reaction with this iron species up here in oxygen. The iron species gets oxidized, and this oxygen species gets reduced to create this superoxide anion. And that is what reacts to create another molecule of oxygen, as well as those two hydroxide, hydroxide, and hydroxyl-free anions. So very similar in how they work. They both have the presence of an iron species, hydrogen peroxide. It's just the actual final steps in how it approaches that, the creation of that uh, hydroxyl-free radical. The second similar reaction I want to discuss is the photoelectro-Fenton reaction. While a lot of this actually is very similar to the Fenton reaction we looked at earlier, the one major difference is that you actually use light to try and reduce that oxidized iron we saw earlier. That was the waste product we saw. In this instance, they're showing it as a iron hydroxide, while earlier we were showing it as an iron oxide. You want to use light to try and reduce that back down to a usable iron catalyst, that Fe2 plus, and the free radical. So this is something that has been employed recently to limit the amount of iron waste in these solutions, and so that you have a more of a rejuvenated catalyst that can continuously work rather than having to collect all this iron sludge, remove it, add some more catalyst. It's wasteful, it's inefficient, and it's more expensive. So by being able to use light to rejuvenate that iron catalyst, you can basically keep the Fenton reaction in a constant state, which has been very useful in actual and practical applications. The last similar reaction I want to touch on is hydroxylation. So hydroxylation is similar to the Fenton reaction, as you are adding a hydroxide group onto an organic compound by using an iron catalyst, and or in the case of hydroxylation, you can use various catalysts. But in this specific situation, you can see how they're similar. So by using the Fenton reaction, you can create the same compound with a free radical that you would using this hydroxylation and iron catalyst. So both can accomplish the same thing. The Fenton reaction free radical is just going to be much more aggressive and work on much more stable compounds. So why is the Fenton reaction favorable in a practical setting? So the biggest proponent, in my opinion, of this reaction is the reagents that it uses and the availability of those reagents. So first you have hydrogen peroxide, which is cheap, can be purchased in large quantities, um, and it's something that's readily available from many suppliers. So it's not something that's difficult to get. You can use it in various purposes. And the other one is that iron species, which can be purchased from a variety of different salts, meaning that it doesn't have to come from one particular source, and again, readily available, easy to get. So by having both of those be excuse me, relatively available, cheap, and accessible, you then basically allow for this reaction to be done in larger quantities, allowing it to be applied to industrial use. There could be similar reactions out there that create these free radicals, but they use um, more expensive components or reagents, mean they're less applicable and aren't used to the fullest extent. So the fact that the reagents are available and cheap is very good for this reaction's applicability. Another advantage of this reaction is that, as I mentioned earlier, that iron species that it can end up as waste, as I showed in the mechanism, it can be rejuvenated under certain conditions. I showed the example with light, using light to rejuvenate that down, reduce that back from its higher oxidation state to its original oxidation state at the iron 2 charge, that which they can then be used again in the reaction almost as a catalyst to continuously affect the reaction. Um, this allows the reaction to be done more effectively and efficiently without producing as much waste, which needs to be maintained and can mitigate the reaction if too much is in the solution. And then lastly, just kind of an example, um, it just has various practical applications in wastewater treatment and other industrial settings. The ability to basically denigrate a organic compound that can be harmful to the public or people is very effective, because Otherwise, if they're very stable, it's difficult to react with, and then you just have to store them or have to deal with them in other more expensive ways. So having a cheap and effective way to degrade those organic toxic chemicals is very useful in an industrial setting. So looking at a more modern case of this being used, I don't want to sound like a broken record, but again, wastewater treatment is the biggest application of the Fenton reaction that we are using it to this day. So this is a little snip from the Applied Catalyst B Environmental Journal, their article discussing its role as an advanced oxidation process in AOP, where you use this free hydroxyl radical to react with, right here they're showing it as a dichlorophenol, reacting it with that molecule, and you can see there's different additions that it takes place here, and or one substitution even. Um, and by doing so, it degrades this compound, this dangerous, organic, and relatively stable compound, by adding this hydroxyl radical and basically adding the hydroxide functional group. You are destabilizing this molecule, allowing for it to be further reacted and basically degraded to something that is no longer harmful. So that is why this Fenton reaction has been so useful recently, and why it's continuously being explored and implored in this wastewater treatment as a means to decontaminate and denigrate dangerous compounds in solution. And lastly, just to point to it, I would like to show my references. Uh, Nothing too special in particular here, but I just wanted to touch note on those, as this is where I found most of my information regarding the Fenton reaction, the electro-Fenton reaction, as well as its applicability in wastewater treatment. Thank you for listening to my presentation. I really do appreciate it. I hope that you learned something about both Mildred Gostling and the Fenton reaction, and I hope that you have a great rest of your day. Thank you.